Hi, this is Ben Ruppik speaking. And in the next 5 minutes, I'd like to tell you how Jason Joseph, Michael Klug, Hannah Schwartz, and I used finger and Whitney moves to untangle knotted two spheres in 4 space. So here's a nice family of 2 knots, so-called ribbon 2 knots in 4 space. And I tell you how you can build one for yourself. Start with this unlink of 2 spheres in S4, drawn in black. And now join them back up together by these blue fusion tubes. And in the 3-dimensional picture we are looking at, it might look like that the blue tubes are intersecting the black spheres. But remember that the ambient space is 4-dimensional. And so what you should think is that the cores of these blue fusion tubes are linking with the black spheres. So Miyazaki had a clever observation on how you can simplify these ribbon 2 knots by adding more tubes to them. So look at the left-hand side here first, please. We attach these red trivial tubes to our black spheres to end up with the 1-component unknotted 2 sphere. And now, even though these blue tubes might look complicated, this picture at the top, they have to be trivial attachments, since there's only one way to stabilize the unknot. So this picture at the top here is an unknotted 2 sphere in 4 space. And now look at the right-hand side where we do everything in reverse. So we attach the complicated blue tubes first. And now these red tubes will unknot my surface. Summarizing what Miyazaki just proved for us, it's that for a given ribbon 2 knot, where you need n many fusions to build it, there is n many additional one-handeds you can add to it to make it into an unknotted 2 sphere. So here I'd like to present a similar lower bound for another unknotting number we studied in our joint project, which we defined in terms of the length of a regular homotopy to the unknot. Such a regular homotopy is a sequence of finger moves followed by an equal number of Whitney moves. And in the following, I'd like to show you a movie of such a regular homotopy from this ribbon 2 knot to the unknot. At the end, we'll have a summary slide with our theorem statement. So let's start in the style of Miyazaki by doing trivial finger moves from the last black 2 sphere to all the others. Each of these finger moves will introduce a pair of double points. So what we are looking at here right now is an immersed 2 sphere. So please forget about the first fusion tube. Just look at this immersed 2-component unlink. And one can show that these specific finger moves introduce relations to the fundamental group of the complement, making it abelian. In particular, in this case, what we're looking at, pi1 of S4 minus this 2-component unlink, is a free abelian group of rank 2 generated by the meridians of these 2 spheres. This means that this first complicated looking fusion tube is actually homotopic to a trivial tube going straight across. And in 4D, homotopy of arcs implies isotopy. So it's isotopic to this trivial stabilization. Now we can retract our first finger and continue inductively by stabilizing these tubes. So as promised, here's the summary slide with the definition and the theorem statement. So to advertise our paper, we define the Casson-Whitney number of a knotted 2 sphere in S4 by looking at the minimal length of a regular homotopy from K to the unknot, where length means counting finger moves in this regular homotopy. And in the movie we just watched, we needed to use at most as many finger moves as we had fusion tubes in our ribbon 2 knot, which is precisely this inequality at the bottom here. So I invite you to have a look at our paper for more upper and lower bounds on this Casson-Whitney number and a comparison to the one-handed stabilization number from earlier. Thanks.